you can say, given the mass of the universe, how big would the black hole be that contained this much mass? It's the size of our universe to our horizon. And it's like, wait a minute, could we be one giant black hole? The average density of matter contained within the size of our cosmic horizon matches right on with what you'd get for a black hole this size. That's intriguing.
So, why does the observable universe's mass and size seem to add up to the recipe for a black hole? Because the universe obeys the same gravity that makes black holes, and the equations quietly enforce this numerical rhyme. In a flat cosmos, the rate at which space expands, the Hubble parameter, sets a natural length scale, the Hubble radius. If you ask how much mass energy sits inside a sphere that big, and then compute the gravitational radius that mass would have, you find a match. That's not a coincidence. It's a bookkeeping identity from the Friedmann equation that ties expansion to energy density. When the density equals the so-called critical density, the Hubble radius equals the gravitational radius of what it encloses. But mathematics matching mathematics is not the same thing as physics equaling physics in every respect. If the numbers align so neatly, what physically distinguishes our cosmos from a genuine black hole? What separates them is not the amount of stuff, but how space-time is arranged and where the boundaries live. A black hole's horizon is a trap. All future paths of light and matter tilt inward. It's a localized region in a larger, typically asymptotically flat space-time, with an event horizon defined as a global boundary beyond which future light cannot reach distant infinity. Our universe has no outside and no infinity to escape to. It's a self-contained space-time whose distances are stretching, and the horizons we talk about in cosmology, the Hubble sphere, the particle horizon, the event horizon, are about what we can observe or influence, and they evolve in time. In a decelerating era, galaxies once beyond the Hubble sphere drift into view. In an accelerating era, some drift out. No one is being dragged inward by a central well because there is no center. Can we check that difference with evidence, using light, structure, and time to tell which world we inhabit? We can, and we have. The cosmic microwave background is a fossil glow from a time when the universe was hot, dense, and opaque, not a signal of light trapped by a gravitational prison. Its pattern of acoustic peaks encodes sound waves in a young, expanding plasma and matches a uniform, nearly flat universe governed by general relativity, not the extreme gradients of a black hole interior. Baryon acoustic oscillations mapped across galaxies today align with that same early soundtrack, confirming a history of expansion and cooling rather than collapse. We observe gravitational lensing around galaxies and clusters, yet on cosmic scales, the distance redshift relation, the growth of structure, and the CMB all indicate an expanding spacetime with no evidence for a globally trapped surface enclosing our region. And the reason we cannot see earlier than roughly 380,000 years after the beginning is not because light cannot escape, but because atoms had not yet formed to let photons move freely. These are crisp, testable differences. Could the Big Bang still be the inside story of some larger collapse, a white hole, or a universe born in a black hole elsewhere? That idea is imaginative, but when you press it with physics, it unravels. The time reverse of a black hole, a white hole, would spew matter and light outward, formerly the time reverse of collapse, but such objects are generically unstable and would require extraordinarily fine-tuned, low-entropy initial conditions unsupported by observation. The Big Bang is not an explosion in space or an ejection from a point. It's a moment when every region of space was hot, dense, and expanding, with a remarkably low initial gravitational disorder. Roger Penrose called this the low-wow curvature hypothesis. Our early universe had very tidy geometry compared with the tangled curvature inside a black hole. There are speculative models where a collapsing star in some meta-universe seeds a new cosmos in its core, but they require departures from standard physics or features we don't observe, like specific imprints on the microwave sky or violations of known energy conditions. The clean fit of our data, nuclear abundances, the CMB, large-scale structure, gravitational wave speeds, says we live in a smooth, expanding space-time with horizons that reflect history and future expansion. not a trap set by an external space. The striking numerical match between mass, size, and gravitational radius is a lesson in how geometry and energy are welded together by general relativity, not a sign we've misidentified our home. What the comparison really teaches is that the same equations govern both collapse and expansion. Boundary conditions decide the story, and our story is one of growth, not confinement. Like if this was interesting, and hit the subscribe for more.